Welcome to another podcast. In this example, we're going to be calculating the Maclaurin series for two important series, e to the x and cosine x. Let me just remind you of what the Maclaurin series is. So in the previous video, we derived the Maclaurin series for a function f as being the series with coefficients, the nth derivative of the function evaluated as 0 divided by n factorial times x to the n. And so we want to come up with a similar representation for the functions e to the x and cosine of x. And so we'll start here with e to the x. E to the x at 0, it's e to the 0, which is 1. And then if you look at the derivative of e to the x, you get e to the x. And so once again, taking its derivative there is also 1. And nothing's really going to change here. So if I just keep going, in general, the nth derivative is also going to be e to the x. Therefore, the nth derivative evaluated at 0 is still 1. So if I'm looking at my Maclaurin coefficients here, the Maclaurin series coefficients would be the derivative evaluated as 0 is just 1, and so for e to the x, the coefficients are just 1 over n factorial. So what this implies is the function e to the x has a Maclaurin series. It's one of the easiest and most important Maclaurin series of the form 1 over n factorial times x to the n. So this is the Maclaurin series for e to the x. Alright, so let's go ahead and shift gears now and look at cosine of x. And so if my function is now cosine of x that I want to look at, then looking at its value at 0 is cosine of 0, which is 1. And then similarly, if I look at the derivative here, I got minus sine of x, and the derivative there at 0 would be minus sine of 0, which is 0. So keep going until we recognize a pattern here. So this is minus cosine is the second derivative of cosine. And so we get minus cosine of 0, which is negative 1. The third derivative is positive sine, so sine of x. And so evaluating that at 0 will give 0. And then if I did one more derivative, I get back to cosine, which means that these things are going to be changing periodically. And so the fourth derivative evaluated at 0 is the same as the function evaluated at 0, and that's just 1. And so you can see the pattern here. The pattern here is 1, 0, negative 1, 0, 1. And so the idea is it's hard to describe this just generally for f sub n because you've got to break it down into which n's are even and odd. And so the best way to maybe go about this is writing cosine of x, writing out the Maclaurin series. So the Maclaurin series looks like this. It would be f of 0 plus f prime of 0 over 1 factorial x to the 1 plus f double prime of 0 over 2 factorial x squared, and then it would just keep going. So if I write out those terms, f at 0 is 1 plus f prime at 0 is 0 over 1 factorial times x. The next term would be f double prime is 0, but that's negative 1 over 2 factorial times x squared. Then we would get plus 0 over 3 factorial times x cubed. The next term for x to the fourth would be 1 over 4 factorial x to the fourth, and so on. So you can see here that so these terms are 0, only the even terms survive. And so this looks like 1 minus x squared over 2 factorial plus x to the fourth over 4 factorial. You can see the next term would be minus x to the sixth over 6 factorial, and so on. So that the appropriate way to describe this Maclaurin series would be the sum n goes from 0 to infinity of. It's an alternating series, so it alternates plus minus, so we need that term in there. The numerator is x to an even power, so the way to represent even powers is 2 times n, because even powers are always multiples of 2. And then you're dividing by an even factorial. So here it's technically 0 factorial, and so you're dividing by an even factorial. And so this is the Maclaurin series representation for cosine of x. If I had started this process with sine instead, you can see that all it would have done is shifted the 1 down a spot. So rather than the even terms being 0, the odd terms, rather than the odd terms being 0, the even terms would have been 0. And so I think you can see pretty easily here that the sine Maclaurin series is very, very similar. In fact, the only difference is it's the even powers. So even powers are 1 more than a multiple of 2, divided by the divided by the odd factorials. And so this is a Maclaurin series representation for sine of x. But we have 3 important Maclaurin series boxed here at the end of this video. They are the Maclaurin series for e to the x, cosine of x, and sine x. And all of them have this wonderful property that their radius of convergence is infinity. So the radius of convergence for each one of these is infinity, which makes them all analytic functions and makes them all highly valuable functions in the study of mathematics. All right, thank you for watching.